Hello everyone, my topic is efficient structural casting in large uncertain graphs. This is the outline of my talk. First, I will introduce the background of uncertain graph casting. Next, I will give the state-of-the-art solution. After that, I will discuss our two new methods. And then, I will give the experimental study. Finally, I will do the conclusion. As we know, many real-world networks are often associated with uncertainty, such as protein interaction networks, social networks, sensor networks, traffic networks, and ad hoc mobile networks. I will give one application as example. This figure is the interaction network, and in this network, each node is a protein, and the edge represents the interaction between proteins. Because the environment is noisy, so the interaction between two proteins is unsure. Then each edge is associated with a probability. In the above, I give the application of uncertain graphs. Next, I will model how we discuss how to model the uncertain graphs. And we use the independent probability model. In this model, we assume the probability of each edge is independent of each other. That is, the existence of an edge does not affect the existence of other edges. For an uncertain graph, we can have many instantiated deterministic graphs. We call each graph as a possible word. And if an uncertain graph has m edges, each edge can either be selected in a possible or not. So we can generate 2 power m possible words. The probability of sampling a possible word is calculated as below. In this formula, for an edge E, if it is in a possible word, then the contribution to the model is its probability value. For an edge not in the possible word, then the contribution is 1 minus its probability value. Next, I will give a small graph as example. In this graph, it has 1 edge, so we can generate 2 possible words. The possible word and its corresponding probability are given on the right. Now we finish the modeling of uncertain graphs. Yes, I will introduce the problem definition of uncertain graph clustering. In this problem, a cluster consists of cores and borders. Core refers to vertices that are reliable structure similar to many vertices. Border refers to vertices that are not core, but they are reliable structure similar to a core. And from this definition, we can see we need to know what is reliable structure similar and how many is many. To define reliable structure similar, we need a new measure. We call it probability of structure similar. The formula is given below. The idea of this measure is if two vertices are similar to each other, then the contribution of this possible word is its probability. If not, then the contribution is 0. As a result, this new measure is the sum of all possible words where two vertices are similar. Based on this new similarity measure for two vertices U and V, if its probability of structure similar is no less than eta, then we say they are reliable structure similar. And for vertex U, if it has few or more similar neighbors, then we say it is a core. According to this preliminary, a core is determined by 3 parameters: similarity threshold epsilon, probability threshold eta, and a size threshold mu. And the key to find cluster is to identify core. And then to identify core, we need to compute the probability. of structure similarity for all edges. This is the most important step in the method. And next, I will give an example to illustrate the clustering process. Assume the parameter epsilon is 0.6, mu is 3, eta is 0.26. This figure is the uncertain graph. Then next, we need to compute the probability of structure similarity for all edges. The result is given on the second figure. From the result, we can see there are 11 pairs of vertices. They are reliable structure similar. They are colored by red. And then we can identify 8 cores. The core vertex color is green. Finally, we can get 2 clusters. And now we finish the introduction of problem. Next, I will discuss the state-of-the-art solution. The existing solution uses a two-step framework. The first step is cause detection. In this step, for each vertex, we need to determine if it is a reliable core. After that, we can obtain a set of kinetic components that only contain the core vertex. In the second step, for each non-core vertex, we will assign it into the cluster if it reliable structure similar to one of the core vertex. The state-of-the-art solution is U-scan. In this method, we will compute the probability of structure similarity based on the dynamic programming method. The time complexity of this method is d squared times alpha times m. Here, d is the maximum vertex degree. Alpha is the aberration of the graph. We can see the time cost is very expensive, especially for a large graph. So to reduce the time cost, we propose 2 new methods. The first one is a decomposed approach. We call it pop scan. The main idea is we will break down the computation of probability of structural similarity into 3 components. And each component will contain only one variable. And then each component can be solved efficiently. The time complexity of this method is d times alpha times m. We can see it outperforms the existing solution and is d times faster than the old one. The space complexity is well bounded by m. Next, I will present our second method. The second method is based on the novel index. The core idea is we will index the probability of structural similarity value of all edges for some chosen epsilon value. Based on this index, we can build a time lower and upper bounds of all edges for any epsilon value. First, I will give an observation. Given a uncertain graph G, the parameter mu cannot be larger than the maximum vertex degree d. Then we can easily obtain the set of all candidate reliable cores. And also, for each vertex U, it has a monotonicity property. Specific, given 2 probability thresholds eta 1 and eta 2. If U is a reliable core attained by eta 2, then U must be a reliable core under eta 1. Based on this monotonicity, for each vertex U, we are only interested in the largest probability threshold eta, where U can be a reliable core. And we can prove, or we call such value as a core eta threshold. We can prove, given parameter mu and eta, the core eta threshold of vertex U is the mu largest probability of structural similarity between U and its neighbors. To organize this core eta threshold, we define a label eta order. where this order is the reliable structure-similar order of labels for each vertex U. And here I will give one example, where this example assumes ipsum is 0.6, and this figure shows the neighbor eta order for all vertices. And in this order, we will associate with the probability of structure similarity. And now, in our index, we store the label eta order of each vertex for each chosen ipsum value ipsum. We call our index as UCNO-index. Now we finish the discussion of the index structure. Now, next, I will discuss how to use the index to answer queries. Given the query with parameter ipsum, mu, and eta, we can categorize the query into three cases. The first case is assume there is a ipsum I in the index equals to equal to ipsum. Then, in this case, we can answer query in O m time, and we don't need to access the original path. In the second case, assume there is a ipsum I less than ipsum. Then we can find a time upper bound for all edge. And in the third case, we can find a time lower bounds of all edge. The space complexity is well bounded by M, and the time complexity is optimal when we can find a ipsum I is equal to ipsum. And next, I will give one example to show how we use the index to answer the query. Given the query with ipsum is 0.6, mu is 3, eta is 0.26. And then according to the neighbor eta order, where we have ipsum I equal to 0.6, we can see V1, V2, and V3 has mu or more similar labels, so they are core. And then V4 are similar to V2, so V4 is a border. So this is the result of cores and borders. And now I will report our experimental studies. In this experiment, we use a real-world probabilistic networks. In the statistics are shown in this table. In the first two datasets, the edge probabilities come from real-world application, and in the other dataset, the edge probabilities are randomly assigned. We compare three algorithms in this experiment, where U-scan is the state-of-the-art solution, and then POP-scan is the decomposed-based solution. UCNO-query is the algorithm based on index. And in this slide, we evaluate the performance of different algorithms, and we choose running time and memory consumption as the metric. We assume the parameter is set as both ipsum and eta is 0.5 and mu is 5. The running time of all methods is given on the figure in the left. We can observe UCNO-query is more efficient than POP-scan and is at least 2 orders magnitude faster than U-scan on all datasets. And the figure on the right reports the memory overhead of all algorithms. In general, when the number of edges increase, the memory consumption of all algorithms gradually grows, but the index size of is well bounded. In conclusion, in this talk, we studied the problem of structural casting problem in large uncertain graphs. First, we developed a decomposition-based method, which is theoretical improved complexity. Second, we design a cost-effective index structure and with some powerful permanent strategy. to facilitate the reliable structure similarity computation in a certain graph. So this is all of my talk. Thank you.